Okay, today before we have our lab experiment, we're going to discuss torque. Torque is different than force. When we apply a force to an object of mass m, we get an acceleration a such that net force equals mass times acceleration. Today we're going to learn that when we apply a force to cause rotation, to cause something to twist or turn, then instead of talking about force, we talk about torque. So torque is a description of the effectiveness of a force to cause rotation. Here we see on this particular slide, I want you to notice the diagram at the bottom of the page. Imagine that being an overhead view of a door. So imagine, again, the door is viewed from above, and you'll notice that on the diagram we have the pivot location. That would be equivalent to the hinge of the door. So as viewed from above, that would be the hinge end of the door. The other end of the door, of course, would be where the doorknob would typically be. And the distance in between, labeled D there, is the width of the door, as viewed from above. When we apply a force, F, as shown in the diagram, to the door, it will tend to want to make the door pivot. But the amount of pivoting effect will depend not only on the force and how it's applied, which is called torque, but it also depends on the properties of the door itself and how the mass is distributed about the hinge. We're going to talk more about that at another time, but for today, it's important to note that this force F that's being applied, labeled in the diagram, which I've I'm sketching in there, highlighting in red. If I were to take that force and I were to extend the line along which that force is acting, if I were to just take it and kind of extend that line to infinity both directions, this is called the line of action of the force. Okay, the line along which the force acts is called the line of action of the force. That line of action is important in our understanding of torque because then there's another distance here, which I will label in orange, coming from the hinge or the pivot location down to that line of action in a perpendicular way that gives us what's called the moment arm. So our perpendicular, as shown in the diagram here, is called the moment arm. Now the moment arm times the force is what gives us our torque, or our effective twisting effect. So as far as how effective the door is at the force is to twist, that's called torque, which we use the Greek letter tau for, up at the top of the screen there. And that Greek letter tau stands for torque, and it's our perpendicular, or the moment arm, times the force. So the bigger the moment arm, or the bigger the force, or the bigger both of them, the more torque I have. So we see that it's not only the force that matters here, but how the force is applied. For example, in this particular case, if I were to take that same size force, okay, but I were to apply it along a different direction, such that, for example, if I took the force now and I applied it at the same location, but perhaps in a direction more like that, then when I take the line of action of the force, and now I drop down my moment arm perpendicular to that line of action, I see that I have a much longer moment arm than what I did previously. Okay, I've actually increased the length of the moment arm by applying the force in a little different direction. So same size force, person's pushing the same with the same hardness of force against the door, but the force would be much more effective in this case because the moment arm would be longer. On the other hand, if I apply that same size force in a way that it's closer to the hinge, my moment arm is now going to be shorter and I'm going to have less torque. In fact, if I were to apply the force at the hinge, I would find that it provides me, no matter how hard I push, it would provide me no torque at all because my moment arm here would be zero. So you've probably experienced this effect. I've seen toddler children figure this out, because if you've ever gone to a door that you're unfamiliar with, it has a crash, instead of having a doorknob, has one of those crash bars on it. You may have experienced this on campus when you were unfamiliar with certain doors on campus. On occasion, you can't tell which end the hinge is, and you may start to push on this side of the door to open it, and you may find, oh, it's not opening, and so immediately, most people don't try to just push harder. They realize, oh, I need to push at the other end of the crash bar to effectively open the door. because that same, you can push with a smaller amount of force and it's more effective the longer your moment arm is. And so R perpendicular times F is our moment arm, or is our torque, excuse me. Notice also, though, that because of the geometry here, if this angle theta, labeled in the diagram here, if I take a look at this geometry, this would be angle theta as well. And so distance d times sine of theta, right, would also give me the length of the moment arm. So d times sine theta is the same thing as r perpendicular, and so therefore another way that I can actually calculate torque, as shown at the top of the page, is to actually take the distance from the hinge to where the force is acting, take that distance d, multiply it by the force, and then take the angle between the d and the line of action of the force, which we call theta. So we have a couple ways, several ways here, or a couple different things to think about with torque. We have a couple different ways we can calculate it, but torque is certainly an important concept and idea, and we're going to continue to talk about that and discuss it in today's experiment. Now again, when we apply a torque to an object, it causes rotation. And so this is a little different than F equals ma. Earlier in the semester, we said that if we applied a net force to an object of mass m, we would get an acceleration a, such that the direction of the net force and the acceleration were in the same direction. Now when we're dealing with things twisting, we no longer can talk about force, we have to talk about torque. And instead of talking about mass, it's not only the mass of the object, but how the mass is distributed about the center of rotation. For example, if it has a lot of mass far away from the center of rotation, that can cause some sluggishness in rotation. Whereas if the mass is more concentrated towards the axis of rotation, the object will be somewhat easier to spin. And so we call this property not mass, but we call it moment of inertia, or rotational inertia, and it is in units of kilograms square meters. Two different terms can be used. Moment of inertia typically is the standard, but oftentimes you will hear people talk about rotational inertia, which is another way to describe it. And this rotational inertia I, we will discuss more in a future lecture class. Instead of acceleration A, we now have to talk about angular acceleration, because when something is rotating, it's no longer moving a direction, a translational direction, such that we can measure its acceleration in meters per second squared, but rather because it's turning, we might describe it as so many degrees per second squared, or usually we use the units of radians, and so we would describe the angular acceleration here in radians per second squared. Okay, so basically our equation for F equals ma has now become, in rotating system, we replace force with torque, we replace mass with I, and we replace A with alpha. And so this torque equals I alpha equation is basically Newton's second law for rotating systems. Okay, so again, we will talk about this further in a future lecture class. But for right now, recognize that torques will tend to create acceleration that is angular acceleration, or rotation. So this slide just summarizes it quite nicely in a kind of a variable form, and that is that in place of forces in rotating systems, we will now be putting torque. In place of masses in our equations, we'll be putting an I for rotational inertia, or moment of inertia. And in place of A, we will now be putting alphas to stand for angular acceleration. So indeed, our F equals ma equation in rotating systems has become torque equals I alpha. Another important thing for us to understand related to today's experiment is this idea of static equilibrium. When things are in equilibrium, that means that they're balanced. Static equilibrium is a particular type of equilibrium wherein things are at rest. And by at rest, anytime you hear the word static, you should think at rest or not moving. So static equilibrium is a special type of equilibrium. There are two particular conditions that are required for a total static equilibrium. We can have translational static equilibrium without having rotational equilibrium, or we can have rotational equilibrium without translational equilibrium. To get static equilibrium, we need both rotational static equilibrium and translational static equilibrium. This slide shows an awesome picture of a rock balancing, and the rock is not moving. It's an incredibly large rock, and although it is precariously perched there, it's not moving, so therefore it is in static equilibrium. It is not translating left or right, up or down, or in or out. It is also not rotating, so it's also in rotational static equilibrium. This rock is in total static equilibrium because it has both satisfied the conditions for translational static equilibrium and rotational static equilibrium. Here we see a slide that summarizes the requirements of static equilibrium. Number one, the vector sum of all the external forces that act on that body must sum to zero. Therefore, as we've been talking in class, a net force on an object equals its mass times its acceleration. If it's not accelerating, therefore the net forces have to sum to zero. So we've already been doing this somewhat throughout the course when we had conditions where there was no acceleration either direction. Those were conditions of equilibrium. Static equilibrium specifically means that the forces sum to give us no acceleration and the object is also not moving. It's translationally, it's at rest. On the other hand, to get rotational static equilibrium, I need the condition under which the net torques acting on the object are zero. That is, I have to have balanced torques. If there are clockwise torques acting on the object, I need an equal amount of counterclockwise torques to balance the clockwise torques, so that the net amount of torque is zero. If that's the condition, then the object is in rotational equilibrium. If it's in rotational equilibrium and not turning, then it's also in rotational static equilibrium. So again, the word static refers to at rest. Equilibrium refers to balanced. And so we have translational equilibrium, which would be an example would be an object moving with a constant velocity in a straight line. That is in translational equilibrium. If it were at rest and has no acceleration, then it's in translational static equilibrium. If an object has no net spinning force on it, but it's spinning, it's still in rotational equilibrium. But if it's in rotational static equilibrium, then not only is the net torque on the object zero, but it's also not spinning. So these are important ideas to distinguish, and one of the things you'll work on practicing in some of the questions for this lab experiment. Okay, so finally, what you're going to be doing here in this experiment is you're going to be taking a meter stick, which is going to balance on a pivot, which we call the fulcrum. Okay, so this place where the meter stick balances is called the fulcrum. Okay, and the meter stick balances on that, and we are going to experiment today by hanging different amounts of mass, maybe M1 here, M2 here, and we're going to see how these things balance. We're going to look at the moment arm. Again, because gravity is our force that's being applied, mg, okay, m1g and m2g. We're going to be able to do this experiment since all the forces, all the masses are going to be accelerated by g, the acceleration of gravity near planet Earth. Then what we can do is just do the experiment in mass. So even though mass isn't a official unit of force, you'll be able to solve out and think of your forces as in grams. So even though the gram is not a unit of official unit of force, it makes things a little easier today if we just list our forces in units of mass here, or grams. So you'll find the masses. You also find the moment arms, which would be the distance from the pivot location, your fulcrum, to where the mass is hung. So your moment arms for this particular experiment can be easily found from the meter stick by taking measurements of the different positions. Okay, you're also going to investigate the center of mass of the meter stick in one part of the experiment. If we think about it, again, our center of mass of our meter stick, if it were a perfectly uniform meter stick, we would expect to be right at about the 50 centimeter point. However, you're going to find with real meter sticks, they may have a little knot in them or something like that, and the grain is a little differently in some parts of the meter stick from others. And so the center of mass may vary a little bit. It may be, half a centimeter off one way or the other from that 50 centimeter mark. So when you find where your meter stick balances, that will establish the center of mass of your meter stick, and you can then really think of the entire mass of your meter stick being concentrated right at that center of mass. So there's some interesting little experiments you'll do today. You'll also try to use your newfound understanding of torque that you'll learn throughout the experiment to actually weigh and measure the masses of some unknown quantities, including the mass of your meter stick. Then you'll use the laboratory balances to compare your answers that you calculated to see how they compare with the actual measurements on the balance. So have fun with the experiment, investigate, question things, try to be careful to get decent results. If you're careful with your measurements, it should work out well. Don't forget to follow the instructions. The mass of the clamps involved in the experiment do need to be accounted for. Just keep in mind that if there's a clamp on at the fulcrum, that is acting at a zero moment arm, and so that mass will not affect the system. While on the other hand, if there's a clamp hanging this mass, the mass of that little clamp must be accounted for as part of this force that's pulling down. So think about it. You got to think it through. It's not hard, but pay attention and you should get very nice results. Have a good lab.